Assalamu alaikum, dear students. Today we will be learning the phenomenon of interference. But before going to interference, let us complete what we started yesterday and we went halfway through. Let us just complete that. We will take a few minutes for that. We were discussing how we can explain or derive the law of refraction of light, that is Snell's law, using Huygen's principle. And we constructed this figure. Just to make a review of what we learned yesterday, this is a surface separating two media A and B, where we consider medium B has more optic density compared to medium A. Therefore, the speed of light in medium B will be less than that of medium A. Then we assume that there are two parallel light rays incident on this surface, and we consider this as one of the incident light ray, and this is another incident light ray. So in the first interval, we assume in a time t1, the light ray travels with the velocity c1 in medium A. So it must have traveled this distance and is incident on the surface at a point A. And in the same time, the light ray which is parallel to it must have traveled c1, t1 and have reached a point D. Now, in the second time interval, that is t2, what happens is this light ray which is incident at A will enter to the second medium. Since it is optically denser, as it moves to the second medium, it turns towards the normal. So the angle of refraction R will be less than the angle of incidence I. And at the same time, T2, this light ray which reached D will continue its motion in the same direction because it is in the same medium and will reach a point B. Then how we constructed the refracted wavefront? The perpendicular joining these two light rays will give you the incident wavefront. So from point A, we have drawn a perpendicular to this ray and got it at D. This is the incident wavefront. Now to construct the refracted wavefront, I told you to take a compass. Yesterday I didn't have a compass with me. Now I have taken a compass. So how to construct that? You have to take this distance dB. So dB is C1 T2, where C1 is the speed of light in medium A. So I'll take this distance with the compass from B to D. So this is C1 T2. I got that distance here. But we know that in the second medium, which is optically denser, the velocity of light will be lesser. So C2 T2 will be lesser than C1 T2. So from what distance I measured here, I have to reduce a little bit. And then I have to draw an arc here. So I have to keep the compass here and draw an arc. And then I get this arc which cuts this refracted ray at a point E. So at this point E, if we connect from B, we will get the refracted wavefront. So this is the refracted wavefront because the light ray reached point B after time interval T2 and the light ray must have reached point A after a time interval T2. So when you draw this line perpendicular, we will find here the refracted wavefront. Is it clear how the refracted wavefront is constructed? Is it clear?
Yes.
Yes. Okay.
Okay. Then we were going to derive the Snell's law. You know the Snell's law states that sin I by sin R is equal to a constant. That constant is the refractive index of medium B with respect to A, because medium P is the second medium. Or the same Snell's law can be written in the generalized form where we say that in this medium the angle is I. And the refractive index, if I express the absolute refractive index of medium A as mu A, it will be mu A sine I is equal to, in this medium, the angle made is R. And if the refractive index or the absolute refractive index in medium B is mu B, this will be equal to mu B sine R. So let us find whether we can get to these two equations by using the concept of wavefront. So for that, first we consider this triangle ABD. And from this triangle, this angle is 90 degrees. So this is a right triangle. And for I, the opposite side is BD. So sine I will be equal to BD divided by hypotenuse, which is opposite to this 90 degree, that is AB. So I got sine I is equal to BD by AB, and BD we know it's C1, T2, and AB I have kept as such. So T1, C2 by AB. Now I'm considering the triangle ABE. From this triangle, we know this angle, that is the angle between the refracted ray and the refracted wavefront, is 90 degree because they are always perpendicular to each other. So this will be the hypotenuse, and opposite side to R is equal to this. So I wrote it as sine R is equal to AB by, sorry, it's not AB, it's AE. AE by AB, and AE is equal to C2T2 divided by AB. Here, I thought you have a confusion why I took R as this angle and I as this angle. I told you that the normal and the surface are perpendicular to each other, and incident ray and the incident wavefront are perpendicular to each other. So the angle between normal and incident ray will be equal to the angle between surface and incident wavefront. Just to show that concept, to make it clear if you haven't used that previously, let me take this. And let me take, this is along the normal and this is along the incident ray. Okay. So this angle is I. Just I am taking like this. Now, if I rotate the normal through 90 degree, I will get the surface. And if I rotate this incident ray along 90 degree, I should get the incident wavefront. So if I rotate these two together to 90 degree, then I will get the angle between the surface and the incident wavefront. So both of them are rotating through the same angle. So the angle between them will not change, right? So if I is the angle between the incident ray and the incident wave, and if I rotate both through 90 degree, the angle between them, now it is between the surface and the incident wavefront also will be equal to I. Is that clear, Zaman?
Yeah, teacher, got it now.
Okay. Similarly, I told that the angle between the incident ray and the refracted ray is R. Now, if I rotate the incident ray through 90 degree, I will get the surface. And if I rotate this refracted ray through 90 degree, I will get the refracted wavefront. So if I rotate them together to 90 degree, I will get the angle between the surface and the refracted wavefront. So that is also R. That is why I took this angle as I and this angle as R. I hope it is clear to you now. So in future, you need not think this much. You can directly apply this concept that if the two angles are rotated through the same angle, the angle between them will be same. So we have reached here. Now what we want to find is sin I by sin R. So taking these two equations, I will get sin I by sin R is equal to this divided by this. So C1 T2 divided by AB whole divided by C2 T2 divided by AB. So divided by AB and T2 gives gets cancelled. So what remains is C1 by C2. Now, you have learned the definition of refractive index in terms of the speed of light. What is refractive index in terms of the speed of light? Refractive index of a medium.
Like the speed of light in C1 divided by speed of light in C2. I mean, sorry. No. C1 is the speed of light, right? C2 is the
Refractive
second
index,
speed of light in the
absolute
second medium.
refractive index of a medium. Do you remember? Yeah, it's C by C, but what comes in the numerator and what's in the denominator? The refractive
The
index.
numerator will be in the first.
Refractive index of any medium is equal to speed of light in vacuum divided by the speed of light in that medium. So absolute refractive index of any medium is the speed of light in vacuum, which we express as C, divided by the speed of light in that medium. Here, the speed of light in A, medium A, we took it as C1, right? So that is equal to C by C1. The speed of light in vacuum divided by speed of light in that medium. Do you remember this definition of refractive index? Okay, so the refractive index of the second medium B is equal to speed of light in vacuum C divided by speed of light in that medium, that is C2 here. So I can take like this. So from this equation I can write C1 is equal to C by mu A. Similarly, C2 is equal to C by mu B. So here in this equation, sin I by sin R is equal to C1 by C2. I'm going to put C by mu A divided by C by mu B. So
The mu1, right?
what?
Mu1.
Mu1 and mu2 I can write. I put this mediums as A and B, right? That is why I took that.
Okay.
Okay, just okay. If you want me to put like this, then from here itself I will. This is medium 2. This is medium 1. This is medium 1. This is medium 2. So I will note this as medium 1. This is medium 2. Okay. So this is for medium 1 and this is medium 2. Okay. So this is medium A is medium 1. B is medium 2. Then fine. If this make more sense to you. So here I have sin I by sin R is equal to sin I by sin R is equal to C1. C1 is C by mu1. C by mu1 divided by C2. So I am multiplying, instead of divided by C2, it will be multiplied by the reciprocal of C2. So into mu2 by C. So C gets cancelled. So this is equal to mu2 by mu1. Mu2 by mu1 means what? Refractive index of 2 with respect to 1. So we got this equation, sin I by sin R is equal to mu2 1. Or in other words, sin I by sin R is equal to mu2 by mu1. So let me rub this part. And I'm going to write here sin I by sin R. Sin I by sin R is equal to, from this equation, it is mu2 by mu1. Either you can write this as equal to mu2 1, refractive index of second medium with respect to first medium, or you can cross multiply. So you will get here mu1 sin I is equal to mu2 sin R. So this is the generalized form of Snell's equation. So we got the generalized form of Snell's equation by considering the concepts of wavefront by Christian Huygens. That is why we say that the Huygens principle can explain the refraction of light. Earlier, I told you that during the time when Christian Huygens proposed this wave theory, what was prevailing was Newton's corpuscular theory, according to which light is a stream of particles called corpuscles. And in that theory, Newton suggested that the light ray will travel faster in a different medium than in vacuum. So the denser the medium, like the corpuscles will travel faster. That was the idea. But it did not match with the experimental results. But when we consider the wavefront concept, we got sin I by sin r. We got it as equal to C1 by C2, right? So sin I by sin r is equal to C1 by C2. We know that when it goes to a denser medium, by the law of refraction, R will be less than I. So if R is less than I, we know that sine 0 to sine 90 means the value will vary from 0 to 1. So larger the angle, larger will be sine theta. So if R is less than I, then sine R will be less than sine R. And from this equation, C2 will be less than C1. So the concept that the light ray will travel with less speed in a denser medium naturally comes from the wavefront concept of Huygens. So this could not be explained by Newton's corpuscular theory, while Huygens' principle could explain the fact that when light travels through a denser medium, its velocity is reduced. So this is one additional advantage of Huygens' principle compared to
Teacher,
corpuscular theory. Yes.
just I is greater than R, right?
Yes, I is greater than R. I have written
Then
R.
sin I will be greater than sin R.
Sin I will be greater than sin R, or C1 will be greater than C2. C1 will
No,
be
if we
greater
multiply,
than C2.
suppose
Yes, Zaman. That was
just
our
see
idea.
sin I by sin R.
Teacher, you wrote sin r
Yeah, like I'm
twice.
saying,
Oh, sorry. Sin R will be okay. I'm sorry. Okay. Now it's okay. So R is less than I means sin
no,
R
teacher,
less than sin I. And then C2 will be less than C1, which means when it enters to a denser medium, what happens? The velocity is reduced. So that is the actual concept. But corpuscular theory explained in the reverse way. But now we know that light, when it enters a medium, its velocity reduces. So the Huygens principle agrees to that concept, or it comes naturally from Huygens principle. Therefore, Huygens principle have this advantage over the corpuscular theory. Still, the scientific world was not ready to accept Huygens principle directly, because the prominent theory put forward by Newton was prevailing that time. And later, a young scientist called Thomas Young shows that light behaves like a wave, because one of the properties of wave, which is called interference, is shown by light. So now we are going to learn what is meant by interference. Interference is a characteristic property shown by every wave. So let us see what is meant by interference. So can you see the screen? Can you see the screen now?
Yes.
Okay. So what is meant by interference of light? Before going to interference of light, we need to clarify what are coherent sources. Two sources of light are said to be coherent if they emit light of same wavelength having no phase difference, or if there is any phase difference, it is maintained all along during the propagation. So what are coherent sources? One concept, they should have the same wavelength. Second one, they should have the same phase, or they should not have any phase difference. Even if they have some phase difference, it should be maintained throughout their propagation. So here you can see some examples of different sources of light. The first one, where you have a blue light, green one, and a red one. So this is a combination of different wavelengths. See, the blue light have a lesser wavelength, green have a bit more wavelength, red has a larger wavelength. So these are combination of different wavelengths. So are these waves given out by the say coherent sources? Can we call those
No.
sources coherent? No, because they have different wavelength. Now here in the second figure, you can see all red lines, but each one of them have the same wavelength. They are of the same color. They have the same wavelength. Such waves which have the same wavelength or they have the same color are called monochromatic. Mono means one. Chro means color or wavelength. So they have the same wavelength. They are of the same color. But are they coherent? No, because they are not in phase, which means they do not have the same phase. They have some phase difference and it is not remaining same as they propagate. So this is also not coherent sources. These light rays are not sent by coherent sources. Now look at this figure. This is the light given out by laser. The first one is an example where light is given by sunlight, which consists of every color. Second one is the light given by LED. LEDs, you know, they give a particular color. They are monochromatic light, but still they are not coherent. Then this is an example of the light rays given out by laser. See, they have the same wavelength and they go up and down at the same time. That is, the angle is same. So they are in the same phase. They have the same phase difference. So is this an example for coherent?
Yes.
Yes. So this is an example for the light coming from coherent sources. Now, in practical cases, it is very difficult to get two sources of light sending coherent light rays at the same time. It's almost impossible to get from two independent sources of light coherent lights. So what we do during experiment is, for experimental purposes, the light emitted from a single source is divided into two sources in such a way that each can be considered as an independent source. Here you can see a light source, a yellow colored light source. Now here you have a screen with one slit. What is meant by a slit? A slit is a narrow aperture or a narrow hole where the width of the hole is very small compared to the length. So that is a slit. So here we have a small slit on a screen. So the light ray comes through the small slit. Then we have placed another screen with two closely spaced slits. So the light rays coming from these two slits acts as coherent sources. So these are not independent sources. Actually, they come from the same source of light. So the light rays coming from them will be of the same wavelength and they will have the same phase, or there will be no phase difference. So this is the way for experimental purpose we create two coherent sources of light. Is this clear to you? What are coherent
Yes.
sources and how do we make that during experiments?
Yes, teacher, clear.
Okay, so let us go forward and see what is meant by interference. So interference is a phenomena where the light rays add up. So due to superposition of light means two light rays add up or combine together. Suppose two light rays come and meet at one point, then what happens is called the superposition of light waves. So due to superposition of light waves emitted from coherent sources, intensity of light increases at some points and decreases at other points. As a result, bright and dark fringes are produced on a plane. Here you can see a light source, and the light coming from this source are made to pass through two slits which are kept close to each other. This figure is magnified. Actually, the slits are very narrow, but for us to see clearly, the image is magnified. So there are double slits in the screen, and so the light rays that are coming from these two slits will superpose. Now, at a distance, if you keep a screen, this is the pattern we obtain on the screen. See here, there is low intensity, that is dark red, and high intensity white, dark red, white. So you can see alternate variation of intensity. And these bands which are having high intensity and low intensity, or bands which are bright and dark, are called fringes. So fringes means just bands. So dark and bright fringes are produced on a plane. So you can see that on a screen. So the alternate variation of intensity of light from point to point on a plane is called the interference of light. So this process is called interference. So when two light rays which are from coherent sources superpose, what we can see is dark and bright fringes or alternate variation of intensity of light. And see, they are almost equally spaced, right? You can see equally spaced dark and bright fringes. So this phenomenon is called interference. This is shown by every wave. When Young's showed that this interference is shown by light also, then it sounded as the confirmation of Huygen's wave theory. So there are some conditions for interference to occur. Let us see what are those conditions. The conditions for interference. The first condition is that light sources should be coherent. So in order to get coherent sources, we are using the same source of light and dividing them into two different sources. Then the amplitudes of the two waves should be equal or almost equal. So the wave should have same amplitude or almost same amplitude, and the sources should be very close to each other. So the slits are close to each other, and the sources should be very narrow. I told you the slits are very narrow holes where the width of that hole is very small compared to the length. Usually we are not able to make out that hole with our naked eye, but if you use a microscope, you can find that hole enlarged. So this is an enlarged image. Is that clear what is meant by interference?
Yes, teacher.
Okay. So
Yes.
Here we get dark and bright fringes, right? The phenomenon by which we get a bright fringe or high intensity light, that is called constructive interference. Now, if we get a dark fringe, that is low intensity, minimum intensity or zero intensity, it is called destructive interference. Let us see what is that. So interference can be constructive or destructive. What is meant by constructive interference? If the intensity increases due to the superposition of two light waves of same wavelength and same amplitude emitted from coherent sources, then the interference is called constructive interference. For example, look at this figure. What do you call the upper part? This upper part, you have learned waves, right? What is called the upper part of this wave?
Yes.
Crest. What do you call the down part?
Trough.
Trough. So here, when these two waves combine, these two waves are in phase, which means the crest comes together. Trough comes together. So if such two waves which are in the same phase join together, superpose or add up, what we will get is a large wave. See, the amplitude gets added up. So this has an amplitude A. This also have an amplitude A. So when they add up, what we get is a resultant wave which has double the amplitude. So how will it look? It will look with high amplitude, means high intensity, bright. So this is how constructive interference takes place. Now look at this figure of constructive interference. Here, this blue and green shows two waves which are moving in phase, which means the crest goes up together, trough goes up together, it goes down together. So when they combine, when they superpose, the result is the red line, which means this is wave of higher amplitude. Now, we know that the intensity of a wave is directly proportional to R. What is intensity? Amplitude square, I think. So the intensity directly depends on amplitude. So the amplitude becomes double, means the intensity is increased. So you get constructive interference or bright color. So if the intensity increases due to the superposition of two light waves of same wavelength and same amplitude emitted from coherent sources, then the interference is called constructive interference. Now let us see what is meant by destructive interference. If the intensity decreases or becomes zero due to the superposition of two light waves of same wavelength and same amplitude emitted from coherent sources, then the interference is called destructive interference. Here you can see the figure. Here you can see a figure where, see, the crest comes here while the trough comes here. And when the crest comes for one wave, the trough comes for the other wave. So if such two waves, they have a phase difference of 90 degree, or we call they are out of phase. So if such two waves combine together, what we get is zero intensity. See, the amplitudes die out. So what we have is destructive interference. The waves are destroyed. So if two waves which are out of phase superpose or combine, it causes the destruction of both waves. And we have destructive interference. We won't see light, which means it will be dark, or there will be minimum or zero intensity. Now look at this figure. Here you have the green wave and the blue wave. They are out of phase. Where the crest of green light comes, the trough of blue comes. So when they combine together, the result is shown by the red line, which means there is no wave, zero intensity, zero amplitude, or destructive interference. So is this clear what is constructive interference and destructive interference?
Yes.
Okay. So this is meant by interference of light. Now, I told you that it was a young scientist called Thomas Young who, with his double slit experiment, showed that light shows interference. So let us see the Thomas Young's experiment. So this is Young's double slit experiment, the apparatus he used. Thomas Young in 1801 demonstrated optical interference by his double slit experiment. See, Huygens put forward the wave theory in 1678, 1600s. So it took almost 150 years to prove his theory experimentally. So Thomas Young demonstrated the optical interference. Optical means light related. So light shows interference by his double slit experiment. What he did was he allowed white light to pass through a slit S. So first he allowed white light to pass through a small slit S0 on a screen. So this is the first screen. So the light comes through the slit, and then the light coming through the slit is further divided into two with a double slit on a second screen. So these two, S1 or S2, are two slits on the second screen. So these two slits acts as sources of two coherent waves. So S1 and S2 acts as two coherent sources. We know one of the condition for interference to take place is that the light should come from coherent sources. So this is how he experimentally prepared two coherent sources. And he made that light to fall on a screen. So when it fall on a screen, what he saw was, he saw minimum intensity, maximum intensity, minimum intensity, maximum intensity, the interference pattern, which is shown by any wave. So this he did with white light. When he used white light, what he got was colored interference fringes. So the interference fringes he got was colored. Now, if instead of that, monochromatic light is used, what is meant by monochromatic? What is monochromatic? Are you there?
Yes, teacher. One
You
color,
forgot?
right?
Yes, Khadija, tell me again.
Mono means one, chromatic means color.
Yeah, single color means what? Single what? Same color, that's right. Same color means same what?
Wavelength.
Same wavelength. So monochromatic light means light of the same color or same wavelength. So if that is used, instead of colored fringes, we will get alternate bright and dark fringes. So is that clear? The experimental arrangement by Thomas Young? Is
Yes,
that clear
teacher.
to you? I know the time is over. That's why you are not focusing now. So I will stop it here. And next class, we will see the relation between, we will learn more about Young's double slit experiment, and we will see these relations of few equations which will be solved on whiteboard. So thank you very much. I will just stop